So this is joint work with Separ Asadi, who's currently at Rutgers University. So let's start off with the basic setting of the problem. You have a multiple bidders, in particular n bidders and n m items. Your goal is to distribute these items between these bidders so as to maximize their happiness. So I'm just telling the problem informally for now. So you have a bunch of items which you want to distribute so as to just maximize the happiness, the total happiness. A bit more formally, you have m indivisible items. So you cannot just divide them. You have n bidders who have some private valuations. So this is a function which gives them how happy they are. But maybe your algorithm doesn't know about it. So I'll get to the private part a bit later. Your goal is to come up with a partitioning of these items such that bidder I gets some set Si of items. And your goal is to maximize the sum of the happiness. Okay. Now the valuations that we are interested in, it could be, there are many, many classes of valuations. So the simplest is maybe additive valuations, where your valuation for a set is nothing but the sum of the individual values of all the items. But they are more complicated, in which we are interested in, more like say submodular valuations, where you have decreasing marginal gains or XOS or subadditive valuations. And the question is, how can we do this, like such kind of combinatorial auction? Okay, let's start off first with a purely algorithmic question. So what happens if I tell you the valuations upfront? So suppose I totally ignore the game theory for a moment. If you knew all the valuations upfront, how would you come up with an allocation in polynomial time so as to maximize the sum of the valuations? So if the valuations are additive, then it's easy. You just allocate each item to the bidder who likes it the most, because different items are not going to interfere with each other. So you can just like allocate each item to whoever likes it the most. But in general, you'll worry like how are even the valuations given to you, because you want it to be polynomial time. And there are m items, so there are 2 to the m possible subsets. For each subset, there could be a different valuation. A usual way around this in computer science that we take is assume some kind of an oracle access. So the most popular is the value oracle, where for any bidder, you can query for any set of items, what's their valuation. So the question now becomes like, can you compute a good allocation using a polynomial number of queries to this oracle? And what's known is that simple greedy algorithms give you 2 approximations when the valuations are submodular. Basically, just give the item to a bidder whoever has the highest marginal value. And already, like Lehman et al. Showed that, yeah, it gives you 2 approximation, where by 2 approximation, I mean, whatever is the optimal allocation, I'll give you an allocation which gets at least half of its welfare. Okay, but if you want to go beyond submodular valuations, turns out you cannot do much using value oracle. There are provable hardnesses. But if you use a more powerful demand oracle, which I'll define in a little bit, then you can even extend to XOS and subadditive valuations, the more general classes. So subadditive valuations are like complement-free valuations. And this was shown by 5G. So the main point is, okay, if you're only interested in the purely algorithmic question, then we know constant approximations. So you cannot do it optimally in polynomial time, but you can do it approximately to a constant factor. The question is, what if we have now strategic bidders? Can we still do anything? Okay, so what's the main question? Our question is this truthful combinatorial auction, where again, you have these m items. You have n now strategic bidders with some private valuations. All that means is this valuation function is some private information, which your algorithm doesn't know, your mechanism. Your goal is to come up with some mechanism, an algorithm, which what this mechanism does is it takes as input valuations of all these bidders. So these are the valuations that these bidders are reporting to you. So it need not be their truthful valuation, but you want to incentivize them to report truthfully. And you want to return how should the allocations be made and what payments each of these n bidders are going to make. So what's happening? Like your algorithm is trying to maximize the welfare, which is the sum of the valuations or the sum of their happinesses. The bidders are trying to maximize individually their valuation minus their payment. You want to set up this entire game or the mechanism in a way such that these bidders have no incentive to lie. So this is the main question of truthful mechanism design. And already this was answered like in work of like VCG, like Vickrey-Clark-Groves mechanism, that in general, this is possible. So these are like some generalizations of second price auctions. However, it's no longer a polynomial time algorithm. So they come up with a mechanism which achieves truthfulness and optimal welfare, but not polynomial time. But we are interested in these 3 objectives. So we want both truthfulness, polynomial time, And we are fine with like some approximation, but we want a good approximation to the optimal welfare. So you cannot hope to get the optimal welfare because even in the purely algorithmic question, in polytime, you could not get it exactly. So these are the three main objectives. And if you drop any of them, then the problem becomes easy, or we already know the answer. Good. So what's known right now? So first, what's known is if you're interested in just the value oracle, the weaker oracle, then in general, you cannot do much. I mean, you have to lose some polynomial in the number of items. But with the more powerful demand oracle, you can get some polylogarithmic in M. M is the number of items approximation. So there was a long line of work over the last 15 years. And the main question which is motivating this entire line of work is, can we get a constant approximation? In general, if you add strategic bidders, then can we still achieve performance guarantees which are close to the purely algorithmic questions? In this work, we don't find yet the answer, but we make some progress. So what's our main result is that for submodular bidders, in fact, even for XOS bidders, we come up with a truthful mechanism, which gives you a log M approximation. So we are basically improving this log M to a log M. So M is the number of items. So that's the main result. But yeah, we still don't know the answer to this question, the constant approximation. Good. So what's the outline? Like I told you about some of these combinatorial auctions. Now I'll give you some preliminaries or tell you about some postal pricing mechanisms. What's our high-level idea of our mechanism and how we do its analysis. So let's start off with a very simple setting. Suppose you just have a single item that you want to allocate and you want to maximize welfare. So this is the simplest setup. We all know that there is this second price auction that we can do, like just give the item to the highest bidder and charge them the second highest price. And it has all the nice properties. In particular, it gives you it's all like polynomial time, it maximizes welfare, and it's also truthful. But now let me give you a different kind of a mechanism for this, which is, if in case you've heard of the secretary problem, it's a secretary problem-based mechanism. So this idea will be useful later for more general problems. So for single items, you can just run second price auction in general, but here's a different one, where what you do is you divide all your bidders randomly into two groups. So maybe half the bidders go in N0 and the remaining half goes in N1. All the bidders in N0, you are going to ignore them. Ignore them in the sense you're never going to assign them the item, but you still ask them to cooperate with you and tell them what's their values. So you're just asking them, okay, I'm not going to give you the item, but could you still cooperate with me and tell me what's your valuation? So they are anyways not getting the item. So it's kind of, they don't have any incentive to lie. Equivalently, I mean, you can think of it, maybe it's kind of like conducting a survey or something. So you ask them their values. But now whatever is the max valuation for bidders in this set N0, you set that as a threshold price. And now sell the item to the first bidder in N1 who's willing to pay this price. And my claim is that this gives you at least a 4 approximation. And the reason is simple, just like the classical secretary algorithm, that with half probability, the second highest bidder arrives in N0, and with another half probability, the highest bidder arrives in N1. So you're going to set the price of the second highest bidder, and then only the highest bidder can purchase it. So you are actually maximizing the welfare with a constant probability. So the expected welfare is up to a factor of 4, close to the second, the optimal welfare. So the reason I'm discussing this secretary-based mechanism is because it will be useful later, and also I think it's relatively less commonly taught in classes. Good. Now this raises a question: do we always have good prices, or was something nice happening about this setup? Okay, so what are fixed price auctions? Now I'm interested in selling multiple items, but let me now ask the question: what if are there even good prices? Do good prices even exist? So what do I mean by good prices? So by a good price, I mean you want to run some kind of a fixed price auction where you give each item a price, some price, which is, so you have M items, so each item gets a price. Bidders arrive in any arbitrary order, doesn't matter. And they take any subset of items that they like, basically the set of items that they like the most. So it's kind of like you walk into a shop, you have a bunch of items which are remaining, and you can buy any subset of them. I get the same happiness minus, and the prices that you pay is just the sum of the item prices that you purchase. And okay, you might, and now you want to do this even for more general valuations, like say submodular, XOS. And okay, in general, it's not clear if you can do this in polynomial time, but this is exactly the demand oracle. So this demand oracle that I had given you, its definition is actually exactly this, that given a bidder and the prices, it tells you what is the set of items that the bidder is going to purchase, the optimal. So now this mechanism is first of all, it's truthful because the prices are not changing. So there's no incentive for bidder to be like strategic or something. They can just take the items that they like the most. And it's polynomial time because each bidder can compute the set just in a single demand Oracle query. And what about welfare? So that depends on like how you set up these prices. But what's known is some folklore result that for submodular XOS valuations, there always exist some prices. So I'm not telling you what are these prices, but there always exist some prices such that this fixed price auction gives you a 2 approximation to the optimal welfare. So this only existence. And just to give you a high level idea, that comes basically the existence of these prices pretty much comes from the definition of XOS valuation, and submodular is just a special case. So XOS valuations are some max over a bunch of additive linear functions, and just from these additive valuation functions, you can read off these prices. So we can assume that, okay, these prices exist. So let's just not worry like how we find these prices. Good. Now I claim that already combining this secretary idea and this fixed price auction idea, you can already get a log M approximation, truthful mechanism. And how do you do it? So with a small probability, so this slide is going to be sometimes like the most technical side, but hopefully you'll follow it. It's a simple idea, just combining the last two, where with constant probability, you just run the second price auction on the entire bundle. So this is just to handle some corner cases of the form where like a single bidder has maybe a very large valuation and all the other bidders are insignificant. So, but in general, what you want to do is that, okay, you randomly partition again these bidders into two groups, N0 and N1. For the bidders in N0, you say, okay, unfortunately, I'm not going to give you the item, but could you still cooperate with me? So this is just to get a rough estimate of what the optimal value is, like the optimal welfare. So just to get the scale of the problem, because a priori, you don't even know, I mean, are you aiming for like a few tens dollars or like, are you aiming for $1 billion? So what's really the scale of the problem? And so this N0, because now there's no single bidder who has like most of the valuation, it gives you a very good estimate of the optimal value. Given this estimate, from the last slide, what you can show is that whatever these optimal prices were, they are only within a polynomial in M. M is the number of items factor of the optimal thing. Kind of the intuition is because any item which is cheaper than this, they don't contribute too much anyways. And nobody's going to buy anyways an item which is more than opt price. So there's a polynomial range for this optimal prices. Now by a simple trick of exponential bucketing, where like, okay, you set the prices as powers of 2, and you guess like one of these prices, there's a 1 over log M chance that you will correctly guess an item's price. And now just by using simple expectation bounds, that you can argue that the expected welfare of this mechanism is giving you a log M approximation. So this is kind of like already matching, getting very close to most of the prior works. But all I'm saying is this is like a very simple mechanism where all it's saying is that, okay, if you have a decent estimate of where the prices lie, you can just by a simple bucketing tricks, you can set up those prices, you can guess the prices, run a fixed price auction, and that's already pretty decently good. Now, the main question becomes like, okay, can we get a better estimate of the bounds on these prices? Can we learn the prices better so that I can hope to do something better? And that's what we basically achieve. Okay. So what's our price learning mechanism? Or like, what are the main ideas? So the main ideas is again, okay, first of all, from the previous slides, you already know, okay, we can pretty much always assume that we roughly know the value of opt because I mean, corner cases can be separately handled easily. And now what we do is, okay, rather than dividing the bidders into just like 2 or small number of groups, we divide them into beta groups where beta is log M. So remember, we are aiming for like a poly beta approximation. So we were aiming for a poly log M approximation to the welfare. So now I'm going to make multiple groups of the bidders. So each bidder falls into one of these groups randomly. And my hope is that, okay, in the beginning, I have a very rough estimate of the prices, maybe like a log M candidate prices. Gradually, I'm going to refine these prices as I proceed in the auction. So from group 1 to group 2 to group 3. And eventually, I should have a very good estimate of the real prices. So what do I start off with? So let's assume opt is M. In the beginning, let's imagine all the prices are set to 1. So they are set to be very low. And I want to gradually increase them. Now, what happens with each group is, to each group, you offer the items at the current price. With a small probability, you actually freeze this allocation. So you give them these items at the current prices, whatever they buy. So you're only offering the items to the bidders in this next group NI, so INI. And otherwise, in most of the cases, all the items which were getting sold. So you basically told these bidders, okay, sorry, I'm not going to give you the item, but so they disappear from your mechanism. But you use this information that because these bidders were willing to purchase items, there were some bidders who were willing to purchase items at the current prices. I want to bump up the prices. I want to increase the prices of these items. So the rough idea of the proof is going to be some kind of a learnable or allocatable lemma, where you argue that at each time step, either your current prices are already good. That's why you already have a decent chance that you'll get a good welfare, or there's a lot of demand for the items and you should be increasing the prices. In which case, in some sense, you're learning the prices better and better. And finally, if you're learning the prices better and better, then by the last round, you'll have a very good estimate of the price. And okay, then you'll be done, basically. So what's the main takeaway is that you can use these fixed price auctions. So these are some kind of just like practice fixed price auctions because, okay, there's a small chance that one of them might be the final allocation, but otherwise these are just practice fixed price auctions, and you're using them as a proxy to learn better and better estimates of the prices, of the real prices. So by real prices, I mean like the existing prices that we know from the fixed price auctions. Good. So now the question is, okay, how do we increase these prices? And the idea is some kind of a binary search. So the rough idea is that, okay, you start in the first group or the first round. In the first group, you have like some logarithmic candidate prices for each of the item. You eventually want to filter them out so that items make progress. So you have like log m candidate prices. In the next round, you want roughly like log m over 2, log m over 4, and so on. So after roughly like log m rounds, you'll have a very good estimate. And what's going to happen is each item is going to take its own path. So for this item, like say the blue item, what happens is you run 2 auctions in the first round with prices B1 and B5. If the items get purchased at B5, you move them to the second half. Like in the remaining auction, you try to search prices only in this higher level window. Then maybe the item gets sold at B5, but not at B7. So in the third round, you refine your search to this space and so on. So that's exactly what you do. So you gradually keep on refining the item prices as you proceed in these groups. And the analysis is based on this lemma that I was saying. Like, so at any point, you have some correctly classified items. So your main lemma is, what we show is that in each iteration or round, basically, you get better and better. So either you are in the learnable case, in which case you are getting a better and better estimate. So if you go from round I to round I plus 1, you still retain pretty much all the items. You have like each item goes to the correct subtree in which its price lies, its real price lies, up to a small negligible loss. Or maybe the current prices, in general, you cannot argue that you're always in the learnable case, because there could be some situations where maybe even although the prices are low, still the real people are getting it. So in that case, you cannot hope to learn the prices, but that's also good for you because you are in then the allocatable case. So here, these prices, people are already going to give you a good welfare. And so the main takeaway is that, yeah, you're always making some progress in each iteration or group. So if you're always in the learnable case, then you are great because by the end you reach the last round, you have a great thing. Otherwise, if you ever become in the allocatable case, then there was a small chance, but decent chance, probably like a beta chance that you are actually going to allocate. So again, you're done. So to conclude, okay, what did we see? That, okay, we get a polylog log m approximation. And the main idea was, okay, inspired, you can say somewhat from secretary problems, ideas from there, using that to maximize welfare. We were using these fixed price auctions to learn prices and price trade to update. There's also been some recent updates. So in a recent work with Sepper and also with Thomas Kesselheim, we've also been able to extend these results, not only to submodular and XOS valuations, but also to subadditive valuations. So we can get pretty much the similar results even for subadditive valuations. And we can slightly improve the XOS valuation from log m cubed to log m squared, but the main thing is for subadditive valuation. And this builds on some very recent work of Paul Duting, Thomas Kesselheim, and Brendan Lucia, where they were studied, again, properties of these prices for subadditive valuations in a slightly different context, but they showed some nice properties of these, the existence of some prices, which we are able to exploit in our mechanism using similar ideas. But the main question which we are interested in, and it's like totally wide open, is can we get a constant approximation, say even for submodular bidders? Just leave aside like subadditive, but so which is still we don't know how to attack. And thank you.